Okay, we will go through the important points in the class 11 physics chapter 7 system of particles and rotational motion. Okay, so what is translational motion? If the all points have the same velocity, okay, in this block the all the points moves with the same velocity. In a pure translation motion at any instant of time, all particles of the body have the same velocity. These p1 these all having same velocity. Okay, that is translational motion. Mm. So here we have the axis of rotation is fixed. So this axis of rotation is fixed. So in a rotational motion, they have the different velocities. Okay, these p1, p2, they are all having different velocities. Okay, that is the difference between the translational and rotational motion. So here we have a top is spinning and the bottom is fixed. Okay. So this position vector r is perpendicular. R is a perpendicular distance from the axis of the rotation. Okay, this is the perpendicular distance. This r. So here we have this oscillating axis of the rotation is changing because this fan is rotating. The axis of the rotation is also oscillating here in this case. So this is a pure translation motion. Here we have a translation and a rotational motion. Both are. This is translation as well as rotation here. Okay. See, if we have the center of mass, if we have a particle of equal mass, then the mass exactly is midway between them. Okay, the center of mass is exactly midway between them. If we have the equal mass, this masses m1, m2, if they are equal, then the center of mass is exactly midway between them. Okay, midway between them. So this is the center of mass because these two masses are equal. R is the position vector. So this is important. If the origin of the frame of the reference, the coordinate system is chosen to be the center of mass, then this sigma mr is 0. Okay, for the given system, or the origin is equal to the center of mass, then sigma mr is 0. See here in this triangle, they are asking to find the center of mass. Okay, in this case the center of mass is different from the centroid of the triangle. Okay, see this is x center, y center. So they are saying the center of mass C is not the geometric center of the triangle. Geometric center means centroid. The center of mass is not the centroid of the triangle for this because these masses are different. Okay, because these masses are different. They are asking why this geometric center is different from the center of mass because of the different masses. Okay, in this case you see this is uniformly distributed. So in this case the center of mass is equal to the centroid of the triangle. This. See here in this case on the centroid of the triangle. So here in this case, this lamina center of mass is centroid of the, because of the mass is distributed equally. And for this kind of case, so there are consider this as like a three blocks, and find the center of mass of the each block, then find the final center of mass x, y, and then the center of mass. So if they have a different masses, then you have to put the mass accordingly. Motion of the center of mass. The center of mass of the system of particles moves as if all the mass of the system are concentrated at the center of mass. Okay, so the center of mass moves as if all the mass of the system is concentrated at the point, and all the external forces are applied to that point. Center of mass movement. So here this is important. The center of mass of the fragments of the projectile continuous along the same projectile path, which should have followed if there were no explosion. Okay, after explosion also the center of mass follows same projectile here, path of the center of mass of the fragment. Even after explosion it follows the same path. This is linear momentum, mass into linear velocity. Vector product of the two vectors. Okay, vector product of the two vectors A and B, a vector product, that is A cross B, is equal to AB sin theta, where theta is the angle between A and B. So the direction of the resultant vector, you can apply the right hand screw rule. Okay, so here that is important. A cross B is not equal to B cross A. This vector product is not, A cross B is not equal to B cross A, but A dot B equal to B dot A. That is a dot product. A dot B equal to B dot A, but A cross B is not equal to B cross A. Okay, this is the direction of the resultant vectors. You can apply how to find the direction of the resultant vectors. So if you take cross product of the same vector, then it will be 0. That is null. A cross A is null. So these are the cross product. C cross K cross I is minus J. K cross I is J. J cross K is I. And J cross I is minus K. So these things are important. J cross I minus K, K cross J minus I cross K minus J. These important things. See, this output of the dot product is a scalar quantity. Okay, but the output of a vector product is a vector. Okay, scalar product, dot product, output of a dot product is scalar, vector product is a vector. Here the direction of the angular velocity. Okay, how to find the direction of the angular velocity? And the resultant is perpendicular to both omega and r. Torque is nothing but moment of force. Torque equal to r cross f. R position vector, f is the force. Tau is the torque symbol. Okay. This is the cross product r of sin theta. Angular momentum is represented using the L symbol. L, angular momentum. R position vector, P is the linear momentum. So this is for the point particle. For extended system, it will be I omega. L equal to I omega. This is the condition for the translation equilibrium. Okay, summation of all four those is equal to 0. Okay, condition for the translational equilibrium. This is for the condition for the rotational equilibrium. Summation of all torques equal to 0 is 0. This is for the rotational equilibrium condition. For the mechanical equilibrium, rigid body is said to be mechanical equilibrium if both linear momentum and angular momentums are not changing with the time. Okay. So the same above condition can be written in all the three directions. Okay, like this, like this. 6 independent conditions. Okay, because x, y, z, if you consider translation motion 3 conditions, rotation motion 3 conditions. Or we use symbol R use for the reaction force. This is for the vector addition. Mechanical advantage. Center of gravity of this object is computed using like this. So for this is for the irregular object. How to find the center of gravity for the irregular object, and this is and also G is the center of gravity for this type of object. This is center of gravity. Kinetic energy formula of m square. Moment of inertia. In rotational motion, mass is equivalent to moment of inertia. Velocity is equal to the omega, the angular velocity. Half mv square is replaced with half iw square. This is for the linear motion. This is for the angular rotational motion. These are the moment of inertia for the different shapes. Okay. We can also derive this formula. Perpendicular axis theorem. Okay, this is applicable only for the 2D shapes. Okay. Perpendicular axis theorem applicable only for the 2D shapes which are plane uphill. Okay. The moment of inertia of a planar body lamina about an axis perpendicular to the plane is equal to sum of the moment of inertia about the two perpendicular axes concurrent. All the three axes should be have a common point, and these two axes should lie on the plane, and the third axis, the moment of inertia about a planar body about an axis perpendicular to the plane. Okay, this is the resultant axis. So here this axis is perpendicular to plane and xy is lying on the plane. Okay, this is 2D. So this axis, these two axes lying on the plane, this is perpendicular to the plane, and both all the three have the same common point here. So you can, using the theorem, you can find the moment of inertia of this body. Okay. Answer you can. Same parallel axis theorem. So the moment of inertia body about an axis equal to the sum of the moment of inertia about the parallel axis passing through the center of mass. Okay, passing through the center of mass and the product of the mass and square of the distance. Okay, the moment of inertia of this is equal to the moment of inertia of the center of mass, this axis, plus ma square. M is the mass of the whole system. A is the distance between this. Okay, from here to here there is a distance from the center of mass to the another axis, parallel axis. So using this theorem you can find the moment of inertia, this example. So here if you see, this is the axis passing through the center of mass. You want to find the moment of inertia about this axis. So this axis equal to the moment of inertia of this passing through the center plus ma square. Here a is r. Angular acceleration symbol is alpha, angular acceleration. So we have a kinematics equation for the linear motion. These are linear motion. Same thing you can write for the angular motion. For these formulas are converted into these for the rotational motion. Okay, this for the linear motion and this is for the rotational motion. See, in these problems, you see how they are converting revolution per minute into revolution per second, how they are converting a linear momentum into the angular momentum. Okay, you have to be careful with these conversions. Okay, see here angular speed is initial linear speed is converted into angular speed using multiplying by 2 pi. Similarly, this. So here how they are converting angular displacement into number of revolutions. Angular displacement divided by 2 pi gives number of revolutions. Okay, these are the translational rotational motion, comparison of the translational and rotational motion. These are the symbols and displacement, angular displacement. Angular acceleration is torque divided by moment of inertia. this formula. So here this formula, from this formula, angular acceleration equal to torque divided by the moment of inertia. See, when you see for the symmetrical and unsymmetrical object, see for the this angular momentum and angular velocity need not be parallel, because for some unsymmetrical object this need not be parallel. But for the translational motion, the linear momentum and linear velocity are always parallel. Okay, this is for the translational motion. For rotational motion, this angular momentum and angular velocity need not necessarily parallel. This is important here. See here, for bodies which are not symmetric about the axis of the rotation, L is not equal to this. So in the z direction, angular momentum need not be in the same. Okay, this is important here for rotational translational motions. Conservation of the angular momentum at various scenarios, how this momentum is conserved. See, this example is very important. It says the velocity is independent of the mass of the rolling body. For this problem, we have three bodies: ring, solid cylinder and solid sphere, roll down on the inclined plane without slipping. So what is the velocity of the each bodies? They are independent of the mass of the body. Okay, so here if see independent of their velocity is independent of the mass of the body. V is independent of the mass. Here this is for the ring velocity. See here there is no mass component here. Okay, here also there is no mass component, here also there is no mass component. So that is why it's important. The rolling velocity is independent. The sphere is the greatest and the ring is the lowest velocity. The sphere comes first on the inclined plane, so that is the greatest velocity, and the ring has the lowest velocity. So important thing is velocity is independent of the mass for this situation. Okay, points to ponder.